So from now on until the end of this lecture, we consider the weak approximation theorem. But first, I want to begin with the motivation. This with the spatial case, and this is called the Lagrange interpolation. And I try to state our main theorem as a generalization, Sorry for the ambiguity. As a generalization of the Lagrange interpolation. And in the lecture notes here, I don't plan to consider it, but in the lecture note, we can also see that how we can conclude the Chinese remainder theorem, or how we can view the Chinese remainder theorem as an analogy of the weak approximation theorem in algebraic number theory. But here, we only consider the first case. And I will also plan to prove that there are infinitely many places. And probably for the next lecture, we will continue that we can also use weak approximation theorem to give a lower bound for the extension degree of the algebraic function field. So for the first motivation, let me remind you the method from linear algebra, which is called Lagrange interpolation. And the problem is here. Given pairwise distinct n plus points in a K is any field. K denotes any field, and their AIs are pairwise distinct. For the evaluation, I will use PW for the pairwise distinct points in K. And for given n points, which are not necessarily distinct, our question is that if there exists a polynomial in the polynomial ring or as a vector space that contains polynomials of degrees at most n. So that means they contain polynomials, their degrees at most n, such that which maps these distinct points to given VIs. And we show the existence and the moreover uniqueness by using some observations from the linear algebra. And one of the ideas to show that such a polynomial exists, we consider the polynomial space that contains polynomials of degree at most n as a K vector space. And here also you call that this is isomorphic to K to the n plus 1 because this is the n plus 1 dimensional vector space. And we consider its dual space. It contains K linear maps from our vector space V to K. And here is the idea work as follows. By using these pairwise distinct polynomials, let me define some linear functions from the dual space which maps the polynomials p of x of degree less than or equal to n to evaluation at AI. And since we are given pairwise distinct points AIs, these functionals form the basis for the dual space V star. Please check. And regarding this basis, we can consider its dual basis in V. And this dual basis indeed determined by degree n polynomials in the form of the quotient of the product of the linear factors x minus aj. For the ith component, it doesn't contain of ai over the differential products of the differences of the constants of pairwise distinct points ais. And here, by the dual, we mean that the inner product of this multilinear map is determined by the Kronecker delta ij. So here by the duality, we must consider this inner product. And since this dual basis, so that means this PI is also linearly independent, forms a basis for our vector space V, we can write any polynomial f of x is a linear combination of these basis polynomials. And this representation is unique. Moreover, the coefficients of this polynomial is determined by with respect to this duality. So that means if we evaluate this polynomial at ai, we get the coefficients fi. And in particular, in the statement of our problem, these coefficients are given as bi's f of x, which is determined by these coefficients, gives us the desired polynomial, and this method is called the Lagrange interpolation. So now we want to restate this problem. Because if we have polynomials, it's quite normal to ask a similar question. Do we have an analogy for the functions? And let me state this problem. in terms of the language of the rational function field, again, we suppose that we are given n plus 1 distinct, pairwise distinct points. So that means we can consider these polynomials as rational places, as pairwise distinct rational places, which are determined by the linear factor x minus ai and given b0, b1 up to bn, since we have considered the evaluation of a polynomial at a given point, we may consider these given bi's as elements in the residue class field for the corresponding places pi. And with respect to this statement, we want to generalize it as there exist the functions that such that when we evaluate it at pi or at ai, we get the outputs bi's. And in the language of the algebraic function fields, we can write this statement regarding the residue class maps from k of x to k. And here recall that z plus z of pi essentially the same thing of z plus pi, and it holds if and only if the difference of z and pi lies in pi. In other words, z minus pi has a 0 at pi. And if we want to generalize this question, actually we will be able to generalize this question to more setting, to more general setting. First, regarding any algebraic function field f over k, instead of considering the rational places, we may consider any pairwise distinct places of any degree. And here, instead of considering f plus 1, we may consider n middle place or n many points. And given functions here, in this case, in our in Lagrange interpolation, in the statement of the Lagrange interpolation, this bi's from the k, but we may consider it in a general setting. So let me denote it in this case xi from the f, or since there this can be from this residue class field, so that means they can be functions from OPI, or if they are not, we will set infinity. But for any functions, given functions, n functions, xi from n, our claim is to show the existence of a function in Z such that z minus xi has 0 at pi. However, so any function can have zeros, but any transcendental should has also at least one pose. So we can generalize this correlation having zeros or poles. And moreover, by regarding the multiplicity, we are allowed to describe this valuation with respect to given integers Ri. So they can be positive or negative. And in other words, we are able to describe a polynomial, a function z, with a pre-described poles and zeros counting the multiplicity. And this will be the statement of the weak approximation theorem. And in the next video, I will give a proof, and it's a bit technical, and we need to consider several steps. But let me finalize this statement, why we call the approximation. Please recall that when we define the discrete valuation map, correspondingly we introduce an absolute value from an algebraic function field by regarding a real number between 0 and 1. And here, if these integers are given large enough, this statement in this tells us for given functions x1 up to xn, there exists a function that are close enough to this given n functions ni, xi's. And this is the reason why we call it approximation. And for the proof, it's quite natural to think about, is it possible to give such an explanation? However, we have some technical issues. The first one, we don't have a finite dimensional vector space in the algebraic function field. Moreover, this k of x, the polynomial ring k of x, is also infinite dimensional. And in this case, unfortunately, we can work with duality in this context. But still, and even though we are not introduced some finite dimensional vector spaces structured in an algebraic function field, it will be possible to prove this theorem again, working with the discrete valuation rings, maps, and places. So see you in the next video. Bye-bye.